this chapter and screencast, we are going to talk about acids and bases. The acids and bases are all around us. They do things like influence the color of different types of plants. So this is a hydrangea. And its color, whether it's blue or red, depends on if the soil is acidic or basic. We run into acids and bases in our kitchens. So for example, lemons are acidic while baking soda is basic. And then Clorox is very basic as well. It's a cleaning agent. Acids are characterized as tasting sour a lot of times, whereas bases are characterized as being bitter, right? Soapy, slippery, those types of things. So scientists set out to classify bases and acids. And the first kind of classification that we had was an Arrhenius definition of acids and bases. This fine fellow here is Savante Arrhenius. And he said, hey, look, acids are just a compound that produce H3O plus ions. And this was in the late 1800s. Right? Then you have Arrhenius bases. And he said, hey, those things are compounds that produce OH minus ions. And both of these, I should give the qualifier, they're in aqueous solutions. And so these are solutions that are in water. All right? Now, he did this because he was kind of trying to figure out neutralization reactions. Neutralization reaction is just when an acid reacts with a base and produces a salt and water. Okay. Now, here's how we look at this. Okay. We have hydrochloric acid here and sodium hydroxide. Hydrochloric acid right here is the acid, right? And then sodium hydroxide is the base. So we've got an acid, we have a base, they're reacting together. And what we're going to find here is that we are going to form a salt and water. So how do we predict what the salt is that we're going to form? We take the cation of the base, which is sodium, and it has a +1 charge. Remember, we look at the periodic table to find that. And then we take the anion of the acid, and that's the chloride right there. We crisscross these down, and that gives us sodium chloride in this case, which is a salt. Now, when they're saying salt, what they're talking about here is an ionic complex, which if we remember, it's a metal and a non-metal, or sometimes we can have ammonia as the exception. So that's what we're going to see there. Now, this was problematic eventually because it could not classify things that we knew were bases that didn't produce OH. For example, ammonium is a base, but it doesn't produce OH. So another model came along. It's the Bronsted-Lowry model. And it's named after Johannes Bronsted and Thomas Lowry. And basically what they said is, look, when you have an acid and base that reacts, the only thing that's transferred is a proton. Okay, so when an acid and base reacts, the only thing transferred is a proton. That's it. So we're always looking where this proton goes, and that's H+. And so they said, look, in a Bronsted-Lowry acid, the H+ is the acid is the H+ donor, okay? It's the one that gives up the H plus. So let's look, right? We have HCl here, okay? When we come over here, we see that HCl has turned into Cl minus. It's gotten rid of its H plus. When we look here at H2O, it's H2O here, but it's H3O plus here. It's picked up an H plus. It's accepted an H plus. So the Bronsted-Lowry base here is an H plus acceptor. Okay, so what we're really looking at is the transfer of a proton. The proton is going from HCl here to H2O here. It forms Cl minus and H3O plus. So this is a way that's more versatile for us to classify acid-base reactions. Okay, and so we call these a lot of times Bronsted-Lowry acid-base pairs. And we're going to talk about that in a little bit more. But I want to give you a definition just really quickly. When you see H3O plus like this, that's called hydronium. Right, and so that's the hydronium ion. Now, let's talk a little more about conjugate acid-base pairs. These differ from each other only by the presence or absence of a proton, which is H plus. Okay, so basically what we do is we say, look, right, this is HNO2, and it's going to give a proton to H2O. That H2O becomes H3O plus, and then the NO2 over here is missing its proton, okay? This is the acid because it gives up its proton, and so this is its conjugate base. Now, the reason that's the conjugate base is because if you look in the other direction, right, this NO2 minus reacts with H3O plus and can form water. And so now all of a sudden it can accept a proton in the reverse direction. We will work on identifying these more, but these are called conjugate acid-base pairs. And so you can see water here is the base and H3O plus here is the acid. So I want to show you a few other examples. When we look at this example, HNO2 plus water, we have NO2 minus. This is the acid. This is the conjugate base. The only thing that's happened is a proton has gotten transferred from here to here. Same thing with NH3. When we look here and H2O, H2O gives up its proton to NH3. That forms the ammonium ion and OH minus. And so that's a conjugate acid-base pair. Now, right, turns out we can have lots of classifications of our different acids and bases. And one of the classifications that we can have is a strong acid. Now, a strong acid will completely ionize in water. And so what does that mean? That means that if we were to look at a flask of this reaction, right, we would not find any HNO3 and water molecules. We would find 100% NO3 minus and H3O plus molecules. That's it. So we say that that equilibrium lies completely over here, right, in this area. I want to remind you, since we're forming ions here, strong acids are strong electrolytes. Right? And you can also have strong bases, and they're also going to dissociate 100%. Okay? And they'll be strong electrolytes as well. Now, let's look at weak acids by comparison. Weak acids partially ionize in water. What that means, if we were to look at HNO2, which is a weak acid, right? It's the proton donor. This is the acceptor. What you're going to find is that over here, right, when you look at a flask, you're not going to have 100% of the conjugate acid and base. You're only going to have a little bit. And the majority is going to stay in this form. So that means the equilibrium lies mostly this way. These are also electrolytes. They're just going to be weak electrolytes. When we look for these, and how we classify these, the easiest way to kind of think about strong acids is that there's 7 of them. Now, I have this table and it's missing 1. So when we look at this, these are our 6 strong acids, and I'm going to tell you the 7th one. We have hydrochloric acid, which is HCl, hydrobromic acid, which is HBr, hydroiodic acid, which is HI, nitric acid, which is HNO3, sulfuric acid, which is H2SO4, and perchloric acid, which is HClO4. These arrows are pointing to the hydrogens that are donated. A lot of times they're called the acidic hydrogens. The one that's missing from this table is chloric acid. Which is HClO3. So my suggestion is that you memorize these. Because all the other acids are weak, and that will help you identify whether they're strong acids and therefore strong electrolytes, or weak acids and therefore weak electrolytes. Now, when we talk about this, it's also important how to just identify acids, period. Acids have a proton generally shown in front. So for example, when we look at HNO3, that a lot of times is referred to as an acidic proton. They have protons in front. Or what you'll see is a COOH in a molecule. Like for example, if we have CH3COOH written like that, this combination of atoms is a functional group. It's called a carboxylic acid. It is a key or a clue that that is an acid. Now, here's the sneaky thing about carboxylic acids. They can look very different, kind of like synonyms. So they can look like it's written there, or they can be shown with a double bond O, OH, or they can be shown as this right here. Now, in each case, it's important to understand that the H on the COOH is the acidic proton. That's the one that gets transferred. These guys here just hang out. They don't get transferred. They're not out in front of the molecule, right? So they're behind here, and so they're not acidic. So the 2 ways that we can identify whether we have acidic protons is if they're out front or if they're part of a carboxylic acid. Now, we can also have strong bases and weak bases. Strong bases are group 1 and 2 metals with hydroxide. Sodium hydroxide is a strong base. It dissociates 100%. And so it is a strong electrolyte. Weak bases do not dissociate 100%, just like weak acids. They are also weak electrolytes. Now, when we look at this, and we look at weak bases, right? If you have anything with a nitrogen in it, it can be a weak base. For example, if we have CH3NH2, that's going to be a weak base. If we have CH3NCH3H, that's going to be a weak base. If we've got CH3NCH3CH3, that would be a weak base. So nitrogen is going to be your context clue there that we're going to have some weak bases. Your strong bases, again, group 1 and 2 metals with hydroxide. Now we can have some other weak bases that have a hydroxide. For example, a tricky one that's shown a lot is aluminum hydroxide. That's a weak base, but it's not a group 1 or 2 metal. Okay, so hydroxide and this NH2, which is called the amine functional group, are going to be your clues that you have bases. Okay. Now, if you were looking at water, you might say, hey, Dr. Pierce, I've noticed that water can act both as an acid and a base. And you would be correct. And that's called amphiprotic. And all that means is it's a substance that can act as either an acid or base. So what does that mean? That means it can either accept or donate a proton. Okay, so for example, here we have water. It accepts a proton. It forms H3O plus, right? So it's acting as a base. But here with NH3, we see that it donates a proton and it's acting as an acid, right? To form NH4 plus here. So in this screencast, we talked about acids and bases. We talked about the Arrhenius definition and Bronsted Lowry acids and bases. We talked about how to identify conjugate acids and bases. And then we talked about strong versus weak acids and bases. If you have any questions, please feel free to stop by my office. I would be happy to help.